actually a little more, it's sort of a specialized circumstance where we can retrosynthetically break a molecule into two equal carbon portions to do a self-condensation. It's actually more common for us to have two different reactants undergo an aldol reaction. If we're not careful about this, though, we can form up to 4 products. So 2 of them can be symmetrical, right, which means they came from the same reactant. 2 could be mixed products, meaning they came from other reactants. So let's just call these aldehydes 1 and 2. This is the 2-carbon acetaldehyde and the 3-carbon propanal. If we imagine the breaks here between the alpha and beta carbons to the carbonyl, right? These are aldol products, so next to the OH is where the break happens. So of the symmetrical products, the one with 1, 2, 3, 4 carbons obviously came from 2 of the 2-carbon compounds. The one with 1, 2, 3, 4, 5, 6 came from 2 of the 3-carbon compounds, so that came from compound 2 and 2. Of the mixed products, we could have compound 2 acting as the nucleophile and 1 as the electrophile, or opposite, compound 1 acting as the nucleophile and compound 2 acting as the electrophile. Remember, the nucleophile is the one that has the connection at the alpha. Okay? The electrophile is the one that makes the alcohol, because its carbonyl group got attacked. So not tremendously useful for us to have a mixture of 4 different products there. So we can, however, make a mixed aldol reaction succeed in good yield if, for instance, only one of the reactants would have alpha hydrogens. Okay? This is sort of going to be our main way of getting a mixed aldol reaction to succeed. So take a look at this compound here. I have 2-methyl cyclohexanone. It has these alpha hydrogens. It also has one alpha hydrogen over here on the next to the methyl group. But remember, when we're deprotonating to make an enolate, we always get the less substituted. Okay, so the less substituted alpha hydrogens are chosen in preference to the more substituted. So these are the favorable alpha hydrogens to remove. That can react to benzaldehyde that has no alpha hydrogens, right? CHO next to benzene. The alpha position in benzaldehyde is the benzene carbon that it's attached to, and there's no H's on that. So this reaction can have really no choice. If we can deprotonate right here, we can selectively get that to attack the aldehyde. It's going to attack the aldehyde preferentially because aldehydes are more reactive to addition than ketones are. So if we do that and we heat it to dehydrate, we can get a good yield, right? 70% of this mixed aldol product, where the alpha beta bond is the new carbon-carbon bond that was formed, alpha and beta to the original nucleophilic carbonyl. Another way to do a mixed reaction could be if I have a beta dicarbonyl compound, right? This is ethyl acetoacetate. We saw that in the last chapter with the acetoacetic acid synthesis. Even though this compound over here, even though cyclohexanone has alpha carbons, these alpha carbons are extra acidic because they're between the 2 carbonyls. They will be deprotonated much faster than the alpha hydrogens of cyclohexanone. So that alpha carbon ends up being the nucleophile. The electrophile comes in cyclohexanone. So here is alpha, here is beta to the ethyl acetoacetate. So the beta carbon, once we've dehydrated, has no oxygens on it because originally that had an OH, but we dehydrated to make the alpha beta unsaturated carbonyl compound. Now, to make sure that that works, right, just like we said, it's best that there's really only one favorable reaction that can occur. If there are multiple possible favorable reactions, you're going to get a mixture of products. So if you have, like we said, a compound that only has one set of alpha hydrogens, we can selectively get that to add to a compound with no alpha hydrogens. But the order of addition is important to prevent the enolate from reacting with itself, from doing a self-condensation. So we start out in our container here with the compound with no alpha hydrogens, and we add our base down there. This base hydroxide here has nothing to do because there are no alpha hydrogens on this compound for it to deprotonate. Then to that solution, we slowly add the compound that has alpha hydrogens. And if we were doing this optimally, we would add this one molecule at a time. If I added just one molecule of this alpha hydrogen compound, it would fall in here, it would get deprotonated, and it would attack. And that's it. Then I could add another molecule, it would fall in here, it would get deprotonated and attack. There would be nothing else for it to do. If I just threw all these things in here together, we could deprotonate this alpha compound, and it could also attack some of this same compound that hadn't been deprotonated yet. That's the problem.